RL Circuit 1. In the circuit below, the EMF is 9 volts, the resistance is 31 ohms, and the inductance is 0.20 Henry. Initially, there is no current in the circuit and the switch is open. Just after the switch is closed, right here, what is the voltage drop across the resistor and the inductor? If the switch is closed for a long time, where T is greater than 10 times the time constant, what is the voltage drop across the resistor and the inductor? What is the current in the circuit when equilibrium is reached? And how much energy is stored in the inductor's magnetic field when equilibrium is reached? Just after the switch is closed, what is the voltage drop across the resistor and the inductor? Right after the switch is closed, the inductor acts to resist the change in the current, and it won't let it change from zero. So you'll have zero current through both circuit elements. We find the voltage drop across the resistance. Well, that'll just be zero because there's no current. Then we apply Kirchhoff's loop rule, and we have E, the EMF, and we have a negative for the voltage drop across the resistor. We're going to take our loop this way in the same direction as the current. Then the convention for the voltage across the inductor, since we anticipate the current's going to increase from 0 to some number, we put a negative here. We do the algebra, and we find all the voltage drop is across the inductor. It is 9 volts. After the switch is closed for a long time, the current will be constant and equal to E over R. So the voltage drop across the resistor is the current times the resistance, so that'll just be 9 volts. And then the voltage drop across the inductor is L di dt. Well, the current is not changing anymore, so that's 0. So you have 0 volts across the inductor. What is the current in the circuit when equilibrium is reached? Equilibrium is reached after a long time, which we typically say is time has to be greater than 10 time constants, and we will mathematically approximate that as t is equal to infinity. So we take our current as a function of time equation, and we substitute in for t infinity. This term then goes to 0, and we're left with E over R, which is 9 volts over 31 ohms, which is 0.29 amps. How much energy is stored in the inductor's magnetic field when equilibrium is reached? We use our potential energy equation, and equilibrium is when we have the max current, which we found on the previous slide. We plug in a number there, and we get 0.0084 joules.